So in part A, we write the formula for the volume of the box. So for the volume of the box, we need the length, width, and height information of the box. We will determine this from this cardboard material. We understand that squares of equal side length, that is x inches, is being cut on the side with length 22 inches. That is, two equal squares are being cut, and we want to find the length of this box. So we can say that this will form this side length will form the length of the box. In fact, this rectangle is also being cut off from the top as well as from the bottom. So to determine this length, what we do is we assume that this length is also x, so that we will have the same height, and this length, this is also x. So this is L and this is L, which means we can calculate 2L. So 2L, this is equivalent to 35. The overall length is 35 inches. And from this overall length, we are cutting off this length of x as well as another length of x, which is basically 2x. So this 2L will be equivalent to 35 minus 2x. And this means the length of the box will be 35 minus 2x by 2. So this is the expression for the length of the box. And now let's determine the width of the box. For this, we have to look at this side, which side length 22 inches. So we know that the total length of this side is 22 inches, and from this, we are cutting off this x length as well as this x length, which means basically we are cutting 2x. So 22 minus 2x will be the width of the box. So we say that the width of the box equals 22 minus 2x. And let's determine the height of the box. For this, we have to look at how we fold this cardboard material. So basically, we fold this like this, and we also fold it like this, which means that this distance or this length will form the height of the box. So therefore, we say that the height of the box is equivalent to x. So all these dimensions are in inches. Now let's write the formula for volume of the box. So therefore, volume of the box, that is V of x, this equals length times width times height, and this equals length equals 35 minus 2x over 2 times width is 22 minus 2x times height is x. So we can simplify this. I'm going to factor out 2, or I just divide this factor by 2 because I can do it here. So this goes 11 times and this 2 will get cancelled. This is 1 time. So basically this expression is now becoming as v of x equals 35 minus 2x times of 11 minus of x times of x. So let's distribute the terms, or maybe we can FOIL these two terms first and then FOIL. I'm going to first distribute x into the brackets and then do the distribution or FOILing out. So we will have v of x equals 35 minus 2x times of 11 times of x is 11x, and negative times of x is x squared. Now let's FOIL this out. So we will have 35 times of 11x plus 35 times of negative x square, and then negative 2x times of 11x, and then negative times negative is positive, so this will become positive 2x times of x squared. Let's simplify this. So this is 35 times of 11x is 385x. 35 times of negative x squared is negative 35x squared, and negative 2x times 11x is negative 22x squared, and this is 2x times x squared is 2x cubed. So we can combine this like terms now. This is negative 35x squared and negative 22x squared. So this will become negative 57x squared. Can mark it here. So therefore we write the final expression I write this x cube term first, so this becomes 2x cube, and then the x squared term, that is negative 57x squared, and finally this x term, which is 385x. So this is the expression or the formula for the volume of the box. Let's now determine the domain of the volume. So for this, we will consider the length, that is the expression for length is, we found out that it is 35 minus 2x over 2, and the width is 22 minus 2x, and height equals x. So we say that all these three quantities should be greater than 0, because we cannot have negative length or negative width or negative height. So therefore that we say that this all three should be satisfied. Length should be greater than 0, width should be greater than, or it cannot be equal to 0, so we can ignore this, should be greater than 0, and height should also be greater than 0. So when we say that height is greater than 0, we see that x has to be greater than 0. That is, the length of the square that we cut should be greater than 0. It cannot, we cannot have any quantity which is less than 0. So this is one domain restriction. And now using these two, length and width domain restriction, let's see what we get. So I'm going to substitute length, that is 35 minus 2x over 2, and this greater than 0. Now we multiply both sides by 2, so we get 35 minus 2x greater than 0. I solve for x from this inequality. So negative 2x greater than negative 35, and divide by negative 2. So remember that when we divide by a negative quantity, we have to flip this sign. So therefore this becomes x less than 35 by 2, and this equals 17.5. That is, x has to be less than 17.5. This is what we get when we set up a length greater than 0. Now let's set up a width greater than 0. That is 22 minus 2x. This has to be greater than 0. So once again, we solve for x from this inequality. So when we do that, we get negative 2x greater than negative 22. So x less than negative 22 divided by negative 2, which is 11. So x has to be less than 11. So we now have two domain restriction, that is x less than 11 and x less than 17.5. So when we combine these two domain restrictions, we have to use only this x less than 11. We cannot have values between 11 to 17.5. For example, suppose if we consider x equals 12, which lies between 11 and 17.5, and when we plug this into the width expression, that is, we have the width expression 22 minus 2x, 22 minus 2 times of x equal to 12. So this will become negative, because 22 minus 2 times of 12 is 24, and this is negative. That is, width is coming as negative. So this is not possible. So that's why we say that this has to be only x less than 11, and we cannot ignore this. And combining these two domain restrictions, that is greater than 0 and x less than 11, we get the domain of the volume as x should be greater than 0 and less than 11. So this is the domain of the volume function. We now answer part C, that is, we have to find the maximum volume and the value of x. For this, we are going to use the volume function, that is v of x. We have 2x cubed minus 57x squared plus 385x. So here we are going to use the first derivative as well as the second derivative test to determine the maximum volume and the corresponding value of x. So first we need to find the first derivative of the function, volume function, so that we can find the critical numbers. So I'm going to take the derivative of this volume function, which is v prime of x, and this equals, we have to find the derivative of each of the terms. We can find it using the power rule. So this becomes a derivative of 2x cubed is 6x squared, minus of derivative of 57x squared is 57 times derivative of x squared is 2x. So 57 times 2 is 114x plus 385 times of derivative of x is 1. So this becomes 385. To find the critical numbers, we set up the equation that is derivative equals 0. That is the first derivative equals 0, and then we find the corresponding x. So therefore, when we set up v prime of x equals 0, we will have this quadratic equation that is 6x squared minus 114x plus 385 equals 0. You can solve this using a quadratic formula. So let's do that. So we say x equal to negative b, which is negative of 114. So this becomes 114 plus minus under the root of b square, which is 114 squared minus 4 times of a, which is 6 times of c is 385, and over 2 times of a, which is 2 times of 6 is so this becomes 12. We can put this 114 plus minus. We plug this into the calculator, and we get under the root of 3756 over 12. So basically, we will get two values of x, that is, we get two critical numbers. So when we simplify this or we plug this into the calculator, we get two values as 4.393. This is one of the value, comma, and the second value is 14.607. So we get two critical values. We have to determine which value of x gives the maximum volume. So for that, we are going to use the second derivative test. So according to the second derivative test, we find the second derivative, that is v double prime of x, and if this is greater than 0 at the critical number, then we say that it is giving a minimum volume, or the volume is minimum. And we find critical second derivative at x, that is at another critical point, and if this comes less than 0 at critical point, we say that the volume is maximum. So we will determine this. So for that, I'm going to take this first derivative, which is 6x squared minus 114x plus 385. So let me copy the first derivative. This is v prime of x equals 6x squared minus 114x plus 385. Let me differentiate this. So I take this derivative, which is the second derivative of the function, volume function. This becomes 12x minus 114. Now we have to take each critical numbers, that is 4.393 and 14.607, plug it into it and check whether it gives greater than 0 or less than 0. So first, let's put the critical number 1, that is x1 equals 4.393 into the second derivative. So therefore, this becomes a v double prime of 4.393, and this equals 12 times of 4.393 minus 114. So clearly we can see that this is 12 times of 4, approximately 4. This will be 48, and 48 minus 114, this will be less than 0. We don't need to calculate the actual value, we just need to know the sign of it. So it is going to be less than 0. And this means at this point, that is at this critical number, at the value of x equal to 4.393, the volume is maximum. We'll also check the other critical number, that is the second critical number, C2 or x2 equals 14.607. So we will put into the second derivative. So therefore this becomes 14.607. This equals 12 times of 14.607 minus 114. and this is going to be 168. If we consider this as approximately 14, this is coming as 168 minus of 114. So this will be a positive quantity. So which means at this point, at this value of x, the volume is minimum. So we can ignore this. Since we are looking only for the maximum value, we need only this value of x. So therefore we see that at x equals 4.393 inches, or approximately 4.4 inches, the volume is maximum. And we can find the maximum volume. So for that we need to plug this value of x into the volume function. So we have the volume function. This is equals 2x cube minus 57x squared plus 385x. I copied this volume function as we figured it out in part A. 2x cube minus 57x squared plus 385x. So we plug this into this volume function. So therefore this becomes V of 4.4. And this gives 2 times of 4.4 cube minus 57 times of 4.4 plus 385 times of 4.4. And this comes out to be 760.85, or approximately, when rounded to whole number, this is approximately 761, and this is in inches cube. So this is the maximum volume of the box. The corresponding value of x is 4.393 or 4.4 inches.